essentially have a big quad mesh of points just from revolving that all the way 360 degrees around the y-axis. And so you can make a lot of geometry that looks pretty good if it has the property that it's spinnable around an axis. Obviously, you can't make a knight that way because it's not. It doesn't have that property, but you can make a pawn that way, you can make a bishop that way, and then you'd have to etch out a chunk of it. You can make a king that way, and then you'd have to add a cross to the top, a rook that way, and then you'd have to add a few things to it, but a pawn is just straight up like that. Yep.
Is there a way to implement the smooth thing that we talked about the other day instead of having a bunch of flat surfaces?
Oh, yes. So let's do that. So this is a program I wrote 1 or 2 years ago called Revolving Profile Example. And it consists of 3 files. The main file, which is chess starter, that goes with graphics.h. Vector.cpp and vector.h, and quadmesh.cpp and quadmesh.h. Vector.h is from our affine math discussion. So it defines a point 3, which is a 3-dimensional point. It also defines a point 4, because occasionally you need one. And it defines a vector, a 3-dimensional vector. And on a vector, you can call the normalize method or the length method. And then it has all these operators that we talked about. You can subtract 2 points and get the vector between them. You can multiply a vector by a scalar and get another vector. Either way, with the vector being on the left or right. You can add a point and a vector and get another point. Both directions. You can subtract a point and a vector and get a point. You can take the cross product of 2 vectors and get a third vector. You can take the dot product of 2 vectors and get a double. You can find the affine sum between 2 points and a double t. That's just the weighted sum. So given 2 points, a start and an end point, and a t between 0 and 1. As t goes between 0 and 1, it will return the weighted point between the 2. That's just an interpolate. Distance between 2 points and adding 2 vectors. So that's a pretty handy kit.
Can I ask why do we even have a point?
Why not just have them both be the same? Just have everything be vectors.
Everything be vectors. A point is really just a vector from 0, 0, 0.
Well,
is it just to help conceptualize it in people's minds, what you're trying to do?
Well, because they are different.
Not really. I mean, you tell me a point, I can tell you that's really just a vector from 0, 0, 0.
Okay.
Right? Am I missing something?
You could say that having a point at x, y, z is similar to having or equivalent to having a vector from 0, 0, 0 to that point, but they're not really the same thing. They behave differently.
I'm just
I would
curious.
argue they're not the same.
Most of the modern programming, like, they don't do points, they only do vectors. So I was wondering if we're doing it for a specific reason. I say modern programming, you look at like Unity, Unreal Engine, I don't think they implement points. Everything's a vector. So I wondered if we were doing it for a specific purpose. I mean, certainly conceptually, it can definitely help you understand that they're different, but am I missing something? Is it, I guess, what I'm really after?
I guess that's the way the book did it.
Okay.
It made a big deal about that they're different, called it affine math. Jessica?
Oh, I was just confused because I thought like points didn't have direction and that was the main difference.
Yeah, vectors are directions and points are just positions in space. That's the main difference. But yeah, you could just call them all vectors if you wanted to and not have two different data types. Okay, so that's what is in vector.cpp and vector.h. Quad mesh, and if you're lusting after this code, I haven't posted this, but the code that I did post has all this in it as well. So you can get your hands on it.
I covet your code.
So quad mesh has a constructor. So given a profile in the XY plane, rotates it about the Y-axis to create the mesh. So you give it a set of XY points and how many there are, and then how many rotations you want. So if you wanted to rotate it, it's going to rotate it all the way around, all 360 degrees. So this is just the resolution. So if you said 36, then it would be by 10-degree increments. And if you said I want 72 rotations, then it would be by 5-degree increments. That's just the resolution. But you just give it the X and Y profiles, and you have to pass in the size because these are arrays. Arrays don't know how big they are. And so what this code does is what we were just talking about. It does the math to do the rotations, and then it builds all the points. And it's a two-dimensional array of points, and so hopefully you guys know that this is the same as in C, except this has 10 points associated with it, and this has yet to have its associated points. You have to call new on this one dynamically, but then after you do, then this and this behave exactly the same. Pointers and arrays are effectively the same in C after you've dynamically allocated your points. Well, if you want a two-dimensional array of points, because I have a lattice of quads, I've got 50 down by 36 rotations or whatever. If I want to dynamically allocate that, then in my header file, I need that. And with a little bit of, this is just one simple new command to make it 10 big or however big you want it on the fly. This is a little bit harder, but you can make a two-dimensional array. The problem with this is you have to say a compile time, it's 50 by 36. Whereas with this, you can make it however many by however many you want at runtime. So that's why it's a star star. It represents a two-dimensional array. It's going to be dynamically determined how big it is, which is basically this by this big. So after I allocated how big it needs to be, rotate all the points around it, then I have a lattice of this many points. And then it's pretty easy to figure out the normals for all of those quads just by taking the cross product of, for one quad, this quad, it's this vector cross this vector is the face normal. So then I figure out how many quads there are and figure out the normals for every quad. And then last time, oops, that's this one, the face normals. And then last time in class, we figured out how to do the point normals if you want to do smooth shading. So if I've got this big lattice of quads, rotating all the way around in 10-degree increments or whatever, then to find that point normal, I just average the 4 face normals and then renormalize it so it's unit big. Now make sure you normalize your normals before you pass them to OpenGL. That won't work good. So then, all that happens basically in the constructor. It fills all this out. And then I can say, draw it flat shaded or draw it smooth shaded. So in my main function, find triangle normal is the same as before. Draw a piece is the same as before. That just loads a chess piece, the ugly ones. Draw axis is new. That will draw at the origin a red line, a green line, and a blue line representing the x-axis, the y-axis, and the z-axis. That's kind of handy. Where's my origin? Which way does x, y, and z go? It's a handy function. Okay, this one you'll want to know. OpenGL has, OpenGL proper has nothing built into it, but GLUT, which sits on top of OpenGL, has some geometry functions built into it. It has one called GLUT solid sphere that will draw a sphere for you. You pass in the radius of the sphere and the number of slices and the number of stacks. That's basically the number of lines of latitude and the number of lines of longitude. It always draws it at the origin, so if you want it somewhere else, first call GLTranslate, and you can put it where you want. So I just bundled it into a draw sphere that takes where you want it, and then I translate it there. And I give it a reasonable number of slices and stacks so that it looks good. Besides GLUT having the ability to draw a solid sphere, I can draw several other basic primitives, including the famous teapot. It's actually called the Utah teapot. Was it originally modeled at the University of Utah? I can't remember why it's called the Utah teapot. We can take a look at that in a minute. You can draw GLUT solid sphere or GLUT wire sphere, wire frame. Same with the teapot, GLUT wire teapot or GLUT solid teapot. So we'll mess with that in a minute and see what they look like. This is code that just draws a profile, so we can see what it looks like in a minute. And then I've got a function called draw a cool pawn and draw a cool sphere. So this is me drawing the sphere as opposed to GLUT drawing the sphere. And I'll show you that they look pretty much the same. But for me to draw the sphere, again, you just specify the radius, it draws it at the origin, But I make my own profile. So that's my X and Y's in the profile. This is horrible programming, but I just gave myself a pretty big number maximum. I should have used STD vectors instead of just making a big array, 500 big. But at any rate, then to make the profile for a sphere, instead of hand specifying them like an artist for a pawn, I just used a formula for a sphere, or for half of a sphere, using sines and cosines. I went from 270 degrees down to 90 degrees to get half of a circle. That's the profile. And then I pass that profile to my quad mesh. And then right now I'm drawing it flat shaded. I could also draw it smooth shaded. Up here I do the same thing for a pawn, but I hand specified a bunch of points just like right there that I thought maybe looked okay for a pawn. Again, pass them to quad mesh, and then I could either draw it flat shaded or smooth shaded, or you can draw the profile if you just want to see what the profile looks like. So you can, individually mess with the profile until you think it looks right. So then in display, I get myself a nice vantage point, set up some lights, 2 colors, one for white and one for black. I draw my axes so I can see where the origin is and which way X, Y, and Z go. I draw the sphere the glut way, and then I draw my sphere right next to it so I can compare them. I draw my pawn. So both of those are using the revolving technique. And then I go ahead and load some pieces the way we did before, the ugly pawns. I switch color to dark and load an ugly king to round it off. So if I run this, make it big. So this one on the right is the glut sphere. The one on the left is my sphere, but it's flat shaded. And then this one here is my pawn, smooth shaded. The sphere is flat shaded, the pawn smooth shaded. And then these 3 are just ugly pieces loaded the way you've been doing it. I can also, for comparative purposes, tell the sphere to draw itself smooth shaded to see how close it is to the glut one. And I'll tell the pawn to draw itself flat shaded so you can see what it looks like. So now my sphere looks a whole lot like the glut sphere. The highlighting is a little bit different. Couldn't get it to exactly match. If I draw the pawn flat shaded, you can see it's a lot more blocky looking. And then if you just want to draw the profile of the pawn, I don't know if you can see that. Can you see that little line right there? So that's the profile of the pawn. And again, to kind of get an idea of taking that and just rotating it up a few times, if you go into the quad mesh code, back to flat shaded. Go into flat shaded for both of them so it'll be easier to see. If I go into my quad mesh code, where I'm drawing it flat shaded, instead of drawing it all the way around, I'm just going to draw 5 of the rotation. animations. So you can see here, it started with the profile, it rotated it just 5 times and flash shaded it. Here, it took the profile and rotated it just 5 of the times all the way around. So you get the idea of how it works. Oh, and there's the axis. It's standard to go red, green, blue for X, Y, and Z respectively. Let's see where the origin is. So questions on any of this? So I'm gonna give you the quad mesh, so you can mess with it if you want to. And the vector code, even though Ken hates it.
I like your vector math. I think the point is redundant, that's all. The vector stuff is awesome.
So as I was kind of like looking into like more of the 3D aspect of graphics and like how to draw objects and stuff, they started talking about like topology and how that like has to do with a lot of the things that we're doing, and I don't know, it just kind of went over my head a little bit. Could you explain like the aspects of topology that we're using?
Now, when people say topology, they could mean a lot of different things. I actually did my doctorate dissertation on topology of modeling, but I'm guessing that's not what you're referring to.
No, I doubt it, yeah.
What do you mean by topology?
Dude, what better question is there?
No. Yeah, asking a question, a PhD,
Yeah.
their dissertation question is a can of worms.
Well,
He said, pick
I'm actually going to show that later on in the semester, along with a discussion of how to get a PhD. That's a useful one, but go ahead.
like specifically they were talking about how like changing how something looks, or I guess like maybe they're talking more about animation, I wasn't really sure. Like if you're changing the vertices, it changes the geometry but not the topology.
Yes. So if I take something that's shaped like a sphere and push it in and out, but it basically is one container in the end with no holes in it, it has the same topology, but different geometry. So this has a topology of an object with one outside and one inside. That has the same topology. Oh, never mind that. That has the same topology, an outside and an inside. But this has a different topology, because now I have 2 separate things with holes in them. So we say this has a genus 1, it's an object with 1 hole. This has a genus 2, because it's 2 objects with 2 holes. So you can have very different geometry with the same topology. It's a 1-hole object.
Does the surface area matter? Like if the surface area changes?
The surface area does not affect the topology. Topology is basically a count of, well, the number of holes.
Okay.
If you're in 2 dimensions. If you're in 3 dimensions, you can do more stuff.
So what aspects of that concept is useful when it comes to graphics?
Nothing that would concern you.
Okay.
If you're modeling things that change topology, like suppose you're doing an animation where 3 separate spheres are moving toward each other And so for the first several frames, they're three separate entities. But then later on, they combine into one glob. Then whoever's rendering this has to be aware of at what point two become one, and then at what point the third one also becomes one with it. Because when you're rendering things, you're drawing a bunch of little triangles here and a bunch of little triangles here, and at whatever point these two join and become one, then you basically have to break that triangle and break that triangle and join it that way with a tube instead, which is what my dissertation was all about. How do you detect when topology changes happen and regeometry it to stitch it back up the right way? But I don't think that's what you were asking.
It was still interesting. My question was kind of random too, so.
I know, like, you picked the right question. Like,
I got all excited. Topology. Okay, so again, this code isn't posted, but I'll show you what is posted, which is basically a superset of this. It's all there if you want it. Google cit.dixie.edu courses. Oops, let me try that again. Courses, 3600, notes. So what is posted is this one, revolving and lighting 2018.zip. So let me show you what's in that file now. I guess I did it 2 years ago, both of these. So again, this one also has the quad mesh code and the vector code. But it has more stuff in it as well. I'll just run it for starters. Oh, I forgot to show you the teapot. There's the teapot. So, what is this one demoing? Aside from this piece, which is